So before we get into inverse orientations, it'll actually be useful to talk a little bit more about rotational representations. We talked before about quaternions and rotation matrices. Another class of rotations is sequential rotations. So let's look at some of those. So this animated GIF video shows rotation about the z-axis, and then another rotation about the x-axis, where this is the new x-axis that has just been rotated, and then finally again another rotation about the new z-axis, which has been rotated twice. The amount of each angle, as shown on the right here, is usually called phi, theta, and psi, and this arrangement of angles and rotations are often called Euler angles, or the Euler angle representation for orientation. While the previous animation showed this ZXZ sequence of orientations, there are other sequences that are pretty common. So for example, the values shown here are the ZYZ, which is a very common one. This equation actually shows a representation for ZYZ, and we have z-axis, which is phi, about the z-axis, and then a rotation of theta about the y, and then a rotation of psi about the z again. And once you take each one of those separate rotations and put them all together, you end up with this rotation matrix for the ZYZ rotation. Here again we use the shorthand of C meaning cosine and S meaning sine, and so it's sine psi, sine theta, etc. Instead of having two axes repeated like the Euler angles, which were ZYZ, ZXZ, XYX, or some other combination of X, Y, and Z where two of the axes are repeated, in these representations each axis is different. So this particular roll pitch yaw rotation has ZYX. Again, we use the same values for phi, theta, and psi, and we have the matrix representation shown here. And when we combine them all together, we end up with this full matrix. When you have roll pitch yaw, the convention is that roll is about the z-axis, pitch is about the y-axis, and yaw is about the x-axis. So very often the roll pitch yaw is used in the aeronautics industry to represent the orientations for an airplane. So if an airplane is flying towards you, then the roll is the rotation about the axis in which it's traveling, yaw is kind of left to the right, and pitch is going up and down in that way. So that's usually what people call roll, pitch, and yaw. There are in fact 12 different possible sequences that are distinct. So we've listed them all here. On the left side we've got what are called Euler angles, the ones where the axes are repeating, and on the right side we've got the Tate-Bryan angles, in which each axis is a different, each rotation is about a different axis, and we have all the different combinations listed here. One thing to note is that essentially this is basically one matrix where we have rows or columns that are swapped. But in every case, there is one element in each matrix in which there is a single cosine or sine that is by itself in a term. So you can see that highlighted here. And then, but in different rows or different columns. And then also along that row for a given value where we had a single member, we have two elements that have just cosine, or a pair of cosine and sine together for each one. Okay, so let's look again at the Euler angle rotation matrix. This is the one for the ZYZ combined matrix. And what we want to do is compare this matrix with the forward kinematics of the spherical wrist. So what we have on this slide, we've got both this is the forward kinematics matrix, and this is the ZYZ Euler angle representation. If we just look at the rotation part of the transformation matrix and then compare the two matrices, we can see that in actuality they look very similar. Every cosine has a cosine equivalent between the transformation matrix from the forward kinematics and the Euler angle representation, and every sine has a sine equivalent on between the two as well. The only difference is that theta 4 is replaced by psi, or phi rather. Theta 5 is theta, and theta 6 is psi. So if you just make that swap between each case, then what we see here is that a spherical wrist is exactly the same as Euler angles. So this can be kind of convenient. So let's take a closer look at the rotation matrix. In the inverse kinematics problem, we start with our goal frame. So we have the rotation component and the translation component, and we've set them equal. And essentially what we want to do with the inverse kinematics again is to find out what angles of our joints will give us this transformation matrix position and orientation. So we want to find out what is theta 4, theta 5, and theta 6. We can examine these two matrices, and some things might pop out. One is that C5 is there by itself alone, and that is essentially equal to R33, since we've got this equation. Every element in one matrix corresponds to the element in the other matrix in the same position. So that C5 is equal to R33 tells us immediately that we can take the inverse cosine from both sides of the equation, and then we'll get theta 5 is equal to the inverse cosine of R33, which is given as part of the problem. The one issue is that taking the inverse cosine means that we have two possible answers. There's a positive or negative component version of the same answer. So what we end up is with two possible solutions. So we filled in theta 5, and we still need to find theta 4 and theta 6. If we again look at the matrix, maybe we can identify other areas which could be useful. And so if you look in the portion just above the one that we just found, we have this cosine 4 sine theta 5 and sine theta 4 sine theta 5. We've got this cosine and sine 4, which we can then use to try to figure out what theta 4 is. We've got cosine and sine multiplied by a constant, this theta 5. We know that we can use a tan 2 and put in some constant for the y value and some constant times the x value, and then determine what our theta 4 is. In this case, the constant is sine theta 5. So we've got sine theta 5 in both cases. We can put sine theta 4 where the y is, cosine theta 4 where the x is, and we end up with theta 4 equal to a tan 2, R23, which is the corresponding position for sine 4, sine 5, and then R13, which is cosine 4, sine 5. But this only applies if the constant is positive. This constant sine theta 5 is positive. If that sine theta 5 is negative, then we have to put a negative sign in front of each of the parameters into a tan 2. But that gives us theta 4. So we have 2 out of our 3 angles solved for. What can we do about the third one? Turns out we can use the same technique that we used for the previous case, where in this case we have, we were trying to find theta 6, and we've got a cosine theta 6 and a sine theta 6 with a almost constant value. There's just this negative value that's prepended onto the first term. So we can take a tan 2 we take the sine value, the sine theta phi value, which is corresponding to the R23, put that as the first term to A tan 2, and then we have this sine, the cosine theta 6 value that's in the R31 position. We put it here, but we add this negative term because there's a negative term there. And then again, this is for the positive case where our constant sine theta 5 is positive, and in the case where sine theta 5 is negative, we have to put reverse the signs on each one of our terms that go into A tan 2. So now we can put it all together, and we have essentially two solutions. We have two solutions because there's the case where sine theta 5 is greater than 0, and the case where sine theta 5 is less than 0. But in each case, you can see it's primarily negative signs, swapping places between those two cases. Then we've got it.